So welcome everyone to our session, the fourth session in our series, Intuitive Introduction to Machine Learning. And this series, we have covered many topics. To summarize, we started with what is machine learning and what is artificial intelligence in the first session. We dealt with some basic statistical concepts. And then in the second session, we went into little bit deeper. We took regression as an example. Regression algorithms. Regression algorithms are algorithms that take an input and they emit out a number. They try to estimate and model some reality, some ground truth reality. Then after that, we did classifier last time. And I took you a little bit deeper, perhaps in the classifier. I brought in a bit of equations and geometry. And explained what is a decision boundary, and we derived the logistic regression equation from first principles. And we ended there. There are many classification algorithms to explore, to have fun with. In the last two sessions, we also did some lab or a code walkthrough to see what does it all mean by walking through data. By the way, my team is, those of you who have logged into the portal have probably gotten access to all the code. Everything that I'm showing is posted to this portal.
At least for me, there's nothing there.
Oh, it is nothing there. Then we'll make sure that it is there. The notebooks that I'm covering, I will make sure. So give me a couple of days. The weekend, my team is, of course, going to take off. So let them come back by Monday, Tuesday, and I'll make sure that all of that shows up.
In portal sign up is through SupportVectors.io.
You go there, you can self-sign up. It's a free course, and all the material is freely available. So, all right. So the topic today is clustering. Clustering, or more appropriately, discovery of clusters or clusters in data. Sometimes when you look at data points in a page, you might notice that they tend to form, like data is not uniformly spread, they form clusters. So one question that we all understand what clusters are. It's a slightly denser concentration of some things, of data points. Right? So a question that comes up is, how common is clustering in data? Now, you realize that if I were to look at, for example, the molecules of water in a beaker, they are not clustered. They are all interacting with each other. They are in a state of Brownian motion. But if I look at typically the children in a playground, you will notice that the children do form clusters. They have a group of friends and they will all be clustered in the playground. So a question that arises is, and that I would ask you guys, how often do data sets present themselves with clusters? Like if you take the set of all data sets in the world from all sorts of fields, geography, chemistry, biology, etc., how often do you think that clusters will be found in the data? 5% of the time, 1% of the time, 10% of the time?
Most of the time.
Oh, and who is this saying that?
Tom.
Oh, Tom Hill. Okay. Anybody would like to contradict Tom? Huh. You have been pretty persuasive, Tom.
But am I right?
We'll find out. Yeah, I'm getting an answer. It depends upon which time.
Yeah, for example, for the LinkedIn or some other social medias, and it's very important to have clusters.
You have a microphone, so everybody can hear you. Lots of remote people. Yeah.
Yeah, I mean, it depends on which kind of app you are building. For example, the LinkedIn or some other social medias, you have some your friends, and you have to be in a cluster.
Yes.
And but for some other apps, for example, the apps I am currently working on, we don't need any clusters.
Yeah. No, the question is slightly different. If you just think the whole population of data sets, so suppose you could just get 1,000,000 data sets. In what proportion of them would you find some form of clusters present?
Pretty much all of the time.
Pretty much all. Yeah. Oh, you guys are all convinced that it's there almost all the time. Actually, you happen to be right. Usually that's not the answer I get from whenever I ask this question, sometimes I get 5%, 10%, 50%, 60%. But actually, and as Tom and all of you are absolutely right, data, unless there is a reason why, data will exhibit clustering. And the reasons are quite interesting, actually. They go to the physics of it. By the way, water, why is it that water doesn't exhibit clustering of the atoms? Well, simply because they have kinetic energy and there's Brownian motion. So any structure is being continually disrupted. Okay? There's dynamics out there. So wherever
the
you
structure
see,
still remains the same. The structure still remains the same.
in water, no.
Yeah.
If you look very closely at any unit space of water molecules, it is continually transforming and buzzing around. Okay? The location of the molecules are continually changing. They are in Brownian motion. So there's an interesting result. I'll give you an idea just to show how predominant clusters are in nature or in real life. You find them in the unlikeliest places. If you go to a social gathering, of course, you notice that after a little while, clusters form, little groups form, right? And that's why in hospitality industry, people are told that if you have a lobby, have lots of little sitting areas segregated from each other. Right? And so it tends to happen in social events. It tends to happen in playgrounds. But it also happens in unlikely ways. When you look at the email, well, these days, it used to be that we used to get postal mails. And it was very apparent. Someday you would carry into your house just 3 letters. Other days it would seem that your mailbox is full. You have a lot of letters that you receive physically. And nowadays it's with messages or emails and so forth. Some days are sparse, some days are heavy. Now you ask yourself that all factors being the same, why is it that some days you get very little traffic, emails or messages, and some days you're just completely inundated with them? And likewise, if you ever stand on top of a highway on a flyover, normal condition says that if there's no congestion in the highway, smooth flowing traffic, then and there's a sufficient density of traffic, they should be all more or less uniformly spaced. That would be optimal. But what you will notice if you ever stand over a flyover is that people come in bunches. Cars, a wave of cars will go by, then there'll be a spacing, then another wave of cars will go by. Right? And it's you may wonder that why is it that this happens? And the reason actually has to do with something in physics. It's called nonlinear dynamics. Whenever lots of factors are at work and there's any kind of nonlinearity or time delay introduced, like human beings have a reaction time to situations that introduces a sort of a latency. And generally in any of these situations, you get what are called chaotic systems. They become chaotic systems. The chaos theory. Chaos doesn't mean random. It means that it's a hidden order. And quite often that hidden order will show clustering. But because nature, most systems in nature is one of the things that people don't realize. Most systems in nature and in finance and in like biology, I mean, of course, that's nature, in physical systems, in financial data, in any form of data, industrial data, they are all broadly governed by chaotic systems. If you study them, you'll realize that there's nonlinearity in them. And they are actually chaotic. Well, the whole planet, our solar system itself is a chaotic system, right? So chaotic systems predominate. And perhaps as a physicist, I would venture that's the reason most data sets also exhibit clustering as a rule. When you don't see clustering, they're there. You can walk into the beach, California beach, and you don't expect clustering in the sandhills, right? It's uniformly spread. But those are not that common. In real data sets, you find a lot of clustering present. So that's one way to look at it. So now the question comes, we in college learn about sorting. Given numbers, we can sort them. There are all these things like bubble sort, quick sort, merge sort, heap sort, and so on and so forth. And clustering seems something like that. Shouldn't it be an easy thing? If there are clusters in data, shouldn't there be an easy algorithm that can identify those clusters? And the problem with that is, there are multiple problems with that. We now know that clustering is actually a very hard problem. It's a NP hard problem. you cannot do it with a deterministic algorithm. And the basic intuition is clustering is at different levels of granularity, right? So for example, let's say that you look at a field and there are lots of sheep there. You might broadly, at a certain gross level of optics, say that, okay, here is one cluster of sheep. But as you near that cluster of sheep, you may now start seeing subclusters of sheep, isn't it? So there's a granularity problem. At what granularity are you looking? Therefore, the number of clusters that you will see changes with that. So, and so clustering is actually a machine learning problem. The way you tackle is using probabilistic approaches. It is under the umbrella of machine learning. It is a pattern matching. It comes under the class of algorithms called a pattern matching. Pattern matching. It is also called unsupervised learning. I like the word pattern matching because it's a little bit more descriptive of clustering. A clustering is a pattern that you're discovering in the data, isn't it? So when you go about finding clusters, why do we consider it an exercise in learning? Why? What form of learning is it? It seems to be just a mechanical thing to do with data. Actually, the reasons are quite interesting, and I'll try to motivate it with an example. Let's say that you happen to be standing somewhere, let's say Market Street in San Francisco, and you're absolutely new there. And you don't have, well, these days everybody has access to a smartphone with maps and so forth, but you didn't have access to it. So what you would do if I were to tell you at some place that you need to head to the beach, right? And you're somewhere in the financial district, you would be hard pressed which direction is the beach, right? But suppose you got the fortune of rising up in a balloon, hot air balloon right then. What would happen? The moment you go, let us say that this is San Francisco Sea Bay and the bridge. Well, there are multiple bridges, but we'll take this. What you notice is that there is a whole region that is, and I'll make very rough diagrams, that is industrial or financial district, commercial district, let's just call it. This is the whole region. And then you come across very rough. Actually, I should have not used green for that, because then there is the Golden Gate Park, the Green Park, Golden Gate Park is here. And again, a very rough picture. And then the rest here are the residentials. Of course, there's some residential here and here also along the sea, but I've oversimplified the picture. Would you agree that this is a very rough and ready picture of San Francisco? Now, if you were to rise up in a hot air balloon, and if you could see this reality, do you think that you have learned something that can help you navigate them? Wherever you are, right? And if I say, head towards the Golden Gate Bridge, you would now know how to do. But more importantly, you are in the industrial zone. Your basic instinct will be keep heading west, right? Because there are three clusters stacked sort of in the north-south axis, and east and west are the sea. You can navigate your way there. So obviously this is a motivating example, perhaps not the best one, but clusters, when you discover clusters, they usually carry a lot of meaning. For astronomers, of course, you can say that the most common thing in astronomy is the discovery of yet another galaxy or cluster, right? Cluster of stars or things like that, right? A galaxy. And of course, looking up at the sky, the fact that we don't see the stars all uniformly distributed, we see them in clusters. That's what makes stargazing such fun. Imagine how boring it would be if all we saw is a palette of randomly spaced stars or galaxies, right? And no galaxies at all. So now the question comes, how do we detect clusters in data? Let us say, let me take a simple example. Let us say that we have clusters like this. And we'll talk about at least two different approaches to clustering. And I deliberately want to bring them. There are many, many approaches to discovering clusters, but I'll deliberately talk only about two of them because they will convey the intuition of clustering well enough. So the problem we are trying to solve is your eyes can see. See, the trouble with human eyes is human eyes as a machine learning, if you think of it as a AI or something that has developed intelligence through a machine learning process, the more you train a machine, the more data you give, the better it gets. That's the one lesson of machine learning. The more data you give it, the more time you give it to learn. These are called the neural scaling laws. You want to make a smarter neural network, bring more data, bring more compute, right? And then you can make a really big neural network and go at it. These are the neural scaling laws. Now, think about the human eye. How many years, the eye itself as a thing, if you think about it, the fishes had eyes. And so did the reptiles, and so did the amphibians and mammals. So it wouldn't be wrong, too off to say that at least 100 million years of data has gone into training the eye in recognizing things, in pattern recognition, isn't it? So think about it, whereas as a contrast, our reasoning ability is far more recent, perhaps 100,000, perhaps 50,000 years ago. We developed pretty good reasoning abilities. And it shows, for example, when you are hiking in a forest and all of a sudden you see, let's take a big cat, a tiger. You don't reason that, see, I'm seeing an animal, it has 4 legs, seems to be yellow, right? Oh boy, it looks like a big cat. Maybe it's dangerous. Maybe it's a tiger. You don't go through the reasoning process. What happens? Your eye sees the tiger, and then you're off trying to survive, trying to run away from it, isn't it? In the blink of an eye, you recognize a tiger. So the pattern recognition is immediate, just as a contrast to our reasoning ability. You can always see that our reasoning, and therefore there are lots of things you will see. We make flawed reasoning decisions all the time, but we rarely mistake a tiger for an orange. Right? Our pattern recognition is almost instantaneous. So when you look at this image, because you're looking at it through eyes, you immediately spot clusters, isn't it? But how do you train a machine to see clusters? That is the problem in machine learning. So there are many, many algorithms. Today we'll talk about k-means. And the other thing we'll talk about is density-based clustering. So let's first talk about k-means. The way k-means does it is quite simple, actually. It basically doesn't discover the clusters. It asks you a problem. It says, I'll solve half the problem. If you know how many clusters there are in the data, I will go find those many clusters. If you say there are 6 clusters, it will nevertheless find 6 clusters, right? So it doesn't know how many clusters there are, but whatever number you give, it will say, tell me what k is. K is the number of clusters. You have to specify that. And if you say 2 clusters, then it will do a very good job of finding 2 clusters. So how does it do that? What it says is randomly pick 2 points. Right? So let us work out the details of k-means clustering. It's quite simple, actually, and it is also one of the most powerful and widespread algorithms for clustering. Okay? Ginormous social graphs like the Facebook graph, right? And a lot of data, news data, etc. They all go through k-means clustering in large AI houses on a continual basis. So it's it is certainly the most popular. So what it says is just pick 2 random points. Now I could pick this point A, is that fair? And B, I could pick anything. So let's pick an easy one. Suppose you're lucky and you pick a point B. Should we say here? You happen to pick this point. Good. So guys, we can see A and B, right? What you do now, so here's how the algorithm works. So first step, start, declare any two points as centroid. And again, the learning will take place. They are actually not the centroid. You claim that what is a centroid? Centroid is the center of gravity, right? Is the center of so many points. If each point has the same mass, centroid very intuitively is the center of gravity, right? It is the dead center of the points. So what you just did is you declared A and B as centroids. But this is wrong, isn't it? You can clearly see with your eyes that this cannot be correct. So we need a way. Remember what we have been learning in the learning is the process of becoming better. How does this algorithm learn and find a better centroid? So the rule is, it says this is step one. And then it says that you do step number two. Let me put step number two next to it. Step two. Every other point asks itself, am I closer to A or B? And if it is closer to A, it belongs to A. If it is closer to B, it belongs to B. Are we together? And so what will happen is, you would agree that, let me take this color. This A will end up owning up to these many points. And B will end up owning all of this. And of course, itself also. Does that make sense, guys? So step two is assign to nearest centroid. Here they are A and B. So that part is also easy to understand. But by now, you must have guessed where this is all leading. The learning part now is very easy actually. You say, okay, now that we have this, we have declared that these are two clusters, imperfect clusters, but these are two clusters. But now what you do is actually compute the centroid of the cluster. Right? In the first time, you just picked two random points and declared them to be centroids. But now it is saying that actually compute the centroid. Step three, now discover better centroids through computation. What are they? Means, right? You take the mean, the average along x-axis, the average along y-axis within a cluster. That is why it's called means, k-means cluster, right? So what will happen? A is going to move. Would it be fair to say that it will move to this point? And B is going to move to this point. Would it be fair to say that? And when it does that, now it seems to be a better situation, isn't it? We can see it. The machine can't see it, but we can see it. And now we ask this question again, that repeat this process. So now that we have the new A, let me call this A prime, and this B prime. So now that we have A prime and B prime, what do? We recluster, we do the reassignment, each point to the nearest. So now what will happen is, in this particular situation, actually, A prime is the points are not going to change loyalties within the cluster, isn't it? Like, you realize that if I move centroid from A to A prime, still the points that belong to A will be the points that belong to A prime in this example, because this was a very clean example. And so when that happens, when you notice that no points are changing, hopping across clusters, or the centroid is not. So now what happens is, if I recompute the centroid, what will happen? I'll pretty much get back A prime, right? So in other words, A prime prime will be the same as A prime. And likewise, B prime prime, the next prime, would be the same as B. So when I repeat this whole step 2 and 3, not much is, the centroid won't move. When the centroid doesn't move, or actually you make it a little softer, when the centroid moves minimally, right, you say, you're done. Are we together? So guys, do you see how simple this algorithm was?
This was no two,
Okay, yeah, two
right?
cluster, k is equal to 2. Here, k is equal to 3. So you take 2k is equal to 2 and you discover these centroids. Now you say, well, it's because you cheated. You took really good points as candidates in the beginning. What if let's take some really bad examples. I'll redraw the cluster more or less. Oh, sorry. In white color. Let's see, white color. I can't reproduce the cluster exactly, but I'll reproduce a fair copy of that. And here was another cluster. And a few other random points. More or less, to the first approximation, these were our previous clusters, isn't it? The data. Now, suppose you have the misfortune of picking A and B horribly. Let's say that you pick A. Let me take this point. This point is A and this point is B. You realize how unfortunate a choice it is. This is A, this is B. Right? Now what happens? A and B, they have a perpendicular bisector, which is this. Let me mark the perpendicular bisector with a different color. Oh, pink should do. Right? B seems to be not winning much. It just got these points, a cluster of just 3 points, itself and 2 other points. A, on the other hand, will end up gaining, let's use another color. A will end up gaining this whole. So I would say A cluster, and this one was B cluster. Now it seems rather bad, isn't it? It looks rather hopeless. But let's go through our step 2 and step 3 and see what happens. We will assign to each point a centroid, a nearest centroid. So between these 3 points of B, you would agree that B prime looks somewhere here. Would you agree, guys? Yeah. B prime is here. But what will happen to A prime? A prime will make a big jump. It will end up somewhere here. Is that fair? Right. So this one moved here and this one moved here. And now you assign, and I'll use a different color. So it is very obvious that the cluster on the right hand side will all go to A prime. What about cluster on the right hand side? Once again, we can do, if you just do a perpendicular bisector. Now what happens is you realize that all things that are, let me use it, if I were to use a different color. Yes. Now this becomes B's cluster and this becomes A's cluster, isn't it? So where will B prime, what will be the B prime prime? Would you agree that it will make a journey because it owns all of these things here? It will be somewhere here, isn't it? It's made a journey from here to here. And what about A prime? It has only a few points from the left cluster, but it has all the points from the right cluster. So it is going to make a journey most likely to this point, A prime prime. Does this make sense, guys?
Question. How many times do we need to
Repeat it? How many times you iterate? You keep iterating till your centroid doesn't move much. Right? You can use all sorts of heuristics. Centroid doesn't move much, or the points are not changing loyalties, right? Things like that. So now what happens is, by now you notice that by the time you end up with centroids B prime prime and A prime prime, you pretty much, it's a home run, right? Because now you don't even need to do further. Maybe you can do one more step to improve upon it. But basically, your clusters are well defined. This cluster is here and this cluster is here, right? And you have gotten pretty good clusters, and there's some points in between. So let's say assign it to that, right? And so K-means actually works quite effectively. Nevertheless, there are some pathological situations where it doesn't work. Right? I'll give you an example. So imagine that your data is like a dumbbell, and you happen to, by utter misfortune, pick these 2 points as your initial choice of centroid. Then what will happen is A and B. A will take this hemisphere, B will take this hemisphere. But when you recompute the centroid, will the centroid move? They won't move. And yet you know that these are terrible clusters, isn't it? Because what was the real cluster? The real clusters were this and this, left and right bells. Right? So we missed that. So there are some pathological situations in K-means. So what you do in reality is you don't run the algorithm once, you run it multiple times, and then you pick the best clustering. But the question arises, what is the definition of best? Because you can't see the data in high dimensions, you can't see the data. So what is your definition of best? And here is one way to look at it. See, and let me take far fewer points to illustrate this. Suppose I have 2, 3, 4 points here, and I have 1, 2, 3, 4 points here. Now, suppose I declare as a worst case situation, this to be A cluster and this to be B cluster, isn't it? So that is a bad choice. A cluster and B cluster. On the other hand, somebody chooses this cluster, let me call it C cluster, D cluster. So has the green effort been more successful or the white effort? Which clustering is better? The green one, isn't it? But what is it about the green clustering that makes it better than the white clustering? If you think about it, you'll realize that there are the interpoint distances, distance between any 2 random points, D point between xi and xj never blows up within a cluster. Within a cluster, the distances are small, isn't it? In the green cluster, the distances between pairwise distances between pairwise distance within a cluster is rather small for green cluster, for green clustering. On the other hand, what can you tell about the white clustering? You realize that let's just look at the top one. This guy, this guy, this guy, this guy. These 2 are near, the 2 right points are near, the 2 left points are near. But what about the fact that you have, oh, sorry, where did the point go? Okay, you have a lot of this kind of distances, right? These distances will be pretty huge. This pairwise distance would be quite huge, right? So this is one. So now we realize that looking at pairwise distances, in some sense, the total pairwise distances, because some distances will still be small, even in the bad clustering. Notice that the 2 left-hand points are close to each other. 2 right-hand points are close to each other. But overall, when you add up all the distances, then it begins to blow up. So you call it, there's a word for it. Now distance, again, it turns out that for similar reasons that we did for regression, you don't want to add up distance, you want to add up all the distance squared, xj, sum up all the distances within ij belonging to a cluster, right? And then sum over the clusters, because you need to find the pairwise distances in one cluster and the pairwise distances in C belonging to clusters. So then you'll get a measure, which is it is called, let me just put, for mysterious reasons, call it WSS. Right? So guys, do you see the intuition? It's very obvious, isn't it? It's just distances, accumulating the distances. And that clearly tells that green clustering is better than the white clustering. And there is a name for it. It is called within cluster sum squared distances. That's what it is, right? Within cluster sum squared distances. S has remained for reasons that I don't know. When people were coining the acronym, they dropped, I suppose they could have called it WCSSD. That would have been perhaps too much. They instead call it just WSS. But the intuition makes sense. So that's how you know. So what you do is you run the clustering algorithm a few times. Let's say you run it 5 times. What will happen is 4 times you'll get it right. 1 time, if the luck is bad, you'll get some weird big number. You can throw that away. And so you can pick the centroids. Every time you do the clustering, keep track of where A is, B is, and what is the WSS value. Right? And then repeat it a few times, and then pick the best WSS, and whatever the centroids are, let them be the real centroids. And to know the centroids is to know the clusters, isn't it? Because every point you assign it to the nearest cluster. That this simple algorithm and very, very effective algorithm is perhaps the most used clustering algorithm in the world. The most used. Now, there are a couple of caveats with this algorithm. It is easy to explain, but it's computationally brutal. Right? Why? Because when you find distances, Euclidean distance between 2 points, when you assign a point to a centroid, how do you do that? You say, am I close to this centroid or this centroid? You have to compute the distance, isn't it? When you compute the distance, those distance computations blow up in higher dimensions. Suppose you have a space of 1,000 dimensions, which is very common these days, right? Text embedding spaces are 1,000 dimensions easily. So now you're dealing with your Euclidean distance has how many terms? 1,000 terms, just to compare 2 points. Right? So k-means needs, while the intuition is easy, in real life, what people do is they accelerate k-means. There's a whole industry, whole set of paper to do accelerate k-means. Some people refer to it as k-means, plus, or whatnot. Right? Many. In other words, some way to accelerate it. I won't go into those ways to accelerate it because those things we cover in a more formal course, a little bit heavier mathematics. But I thought I would leave you with this very simple and elegant clustering approach that just works most of the time. So it leaves one question unanswered though. What is the best value of k? When you look at this data, your eyes can immediately tell you k is 2. Isn't it? But when you have data and you have to discover the clusters, the implicit question is, how many clusters are there in the data? So let us now address that point. What you do is, you do this very brutal compute. The column of your table is k, right? For each k value, so you can take k is equal to 1, 2, 3, 4, and you can go as large as you want, let's say 10, right? And you will see this in the lab actually, in a little bit, we'll see this in action. And then what you do is you compute the WSS. So you realize that when k is 1 here, because these two genuine clusters are far apart, the within some, if you treat the whole thing as one cluster, there will be a lot of big pairwise distances, isn't it? Like for example, if you treat each cluster as a galaxy, the distance between 2 stars, one belonging to this galaxy, one to this, is literally a space travel. It's far, far away, intergalactic travel. And so you will end up with a large WSS value. And so you keep putting the WSS 1, WSS 2, and then of course you keep remembering the centroids. Keep track of the centroids, the best centroids for each of them. So by the way, when you say WSS for 2, it means the best WSS for 2. Even for k is equal to 2, you run it a few times, right? So it becomes the best clustering at each hypothesis. K becomes your hypothesis, how many clusters there really are. Then something very interesting shows up. It is it's a fancy name, but I will just call it the elbow curve. Right? Because what can you say about the elbow? It has a bend, isn't it? Our elbows, we bend our hand at the elbows most of the time. And when you look at the WSS value and you plot k is equal to 1, 2, 3, 4, 5, 6, 7. In this case, what you will notice is WSS will start high. At 2, it will do this. And from 3, it will do this. It will keep going down, right? But that's because at the end of the day, suppose there are 1,000 points. If you take k is equal to 1,000, you'll have perfect clusters because every point is absolutely near itself, right? WSS will go to 0. So that's meaningless. What happens is, in this particular case, where you had data like this, just to remind you what our data looked like, you will notice that if I were to ask you, if this were a hand, where is the elbow? At what value of k is the elbow? You would agree that the elbow is here. Isn't it, guys? This is your elbow. And so you say that elbow is here. Because the elbow is here, you say that the best clustering is at k is equal to 2. Right? That's how you discover the best cluster. And the intuition behind it is simple. The single biggest decrease of falling of k, WSS, it will steeply fall till you have really discovered the number of clusters. But if you further subdivide the clusters, real clusters into subclusters, you will have much slower decrease of WSS because they are all points close to each other. So that is what is used. This is called the elbow method of finding a plot. It's a scree plot, actually, more formally, but elbow method sounds more intuitive, so I'll call it the elbow method. So let us review what we learned. The k-means clustering is a simple algorithm that says, in the beginning, if you tell me how many clusters you want 2 clusters? Okay. Pick any 2 random points and declare them to be the centroid, because we will learn to find better centroid till we can't find any better centroid. You take 2 centroids, you assign each point to the nearest centroid, and then you recompute the centroid. You actually compute the centroid, and you keep doing it till your centroid is not moving much. And then you say, okay, I must be done. Right? That is what k-means is. It comes with a bit of a danger. So you run it a few times, and then the measure of goodness of a cluster is the within cluster sum squared distance. Right? And by the way, some people prefer to, if they are endpoints, some people also prefer to divide it by n, right? So just to average distance, they want to get it. So that also you can stick in if you so want. But it doesn't matter whether you divide by n or not. Ultimately, you're comparing numbers, and you'll get the same scree plot scaled out. Right? So that is a k-means clustering, one approach to do that. Let's look at into another approach.
K-means you always have to
tell how many clusters you want. But you don't. You create a table like this. You start with k, 1, 2, 3, 4, 5. If you don't know k, go through this exercise. Take every possible value of k and draw out a scree plot, elbow plot, and find where's the elbow. That will give you the answer. That will give you optimal k. This is the optimal k discovery process.
What is it supposed to do? What is the business time?
Literally, this is it. WSS. I'll repeat what I said. That is literally it. So the intuition is that distances, pairwise distances, if it is not a cluster, there will be some distances that will be quite large, right? And so all you do is you want to add up the distance. It turns out that you don't add up to make the measure very visible. Square the distances, because when you square a big number, it becomes even bigger. But if you square a small number, it doesn't rise so much. So the difference between a good cluster and a bad cluster becomes far more evident if you add up the squares rather than just add up the numbers. Right? That's why you square the numbers. And it is also for those people who are physics inspired, you would recognize that we are looking at something that is very close to the definition of inertia, right? But we won't get there. Moment of inertia and so on and so forth. But let's not get there. There's another algorithm that I'd like to introduce today. And I noticed that we should be getting into the practical side soon. But humor me. Now look at it as a physicist, as a person who thinks each particle is a grain of sand. Not each particle. Each data point is a grain of sand. Right? So now if you were to think of it like that, and let me draw it out. What would you say about places that are in the cluster versus place that is not in the cluster? What would be the distinguishing quality? Would you agree that suppose I put a page, all of this sand, grains of sand are on a page, that where the cluster is, there is a higher density of sand. Density of sand is higher. Maybe a couple of grains of sand lying here and there also. But clearly where the clusters are, there's a higher density of sand. So a physics approach would be, let us use a density-based approach. Let us discover clusters by looking for areas of higher density. Now the question comes, how do we do that? That's a very good physical intuition. How do we do that? So there are multiple algorithms. There are two that I would like to talk about. One of them is actually the one algorithm that you don't commonly see mentioned, but has a very simple physical intuition. I will start with that. It is called den-clue. Den-clue. Right? What it says is, suppose you consider, so I'll give you a physical intuition because papers don't talk in terms of physical intuition. They talk in terms of a lot of math. But imagine that you're traveling at night, right? You're lost in the forest and you're looking for some city, some civilization somewhere, population center somewhere. You know that population centers will be lit up. Let us say that each point is a bit of a light there, right? And your goal is, suppose you are here, somewhere here. Take a random point, you're here, A. Right? So you are getting light from, let me call this cluster P, cluster Q. They exist, but you don't know. All you know is you're getting light from both the clusters because every point is a source of light. Imagine that it's a source of light. By the way, I'm giving you motivational intuition here so that it's easy. Now you will ask yourself, I'm in the faintest light. In which direction should I move so that there's a maximum increase of light? Right? You would agree that moving downwards is a really bad idea. It's going to get darker. You could go this way also, but intuition says that if you're getting light from this and from this, perhaps the best direction that you should take is to go, maybe in the beginning, you'll want to go a little this because this cluster is a little further, so its light will be a bit fainter, but P's light will be a little brighter. You'll want to move in this direction, the blue direction. Does that make sense, guys? So what you say is, in a more mathematical way, you say that suppose I were to take it as light, but actually there is a more technical something, but I will just say this is the light intensity from each of the points, right? And this is the total light you're getting. You want to go in the direction that gives you the maximum increase of light. Remember, we talked about the gradient. What is the gradient? The gradient gives you the direction of maximum increase of a function, isn't it? Here, the total light is the function. You want to go in the direction that maximizes the light. And so I won't do it. You come here, and then soon you'll realize that next step, so you will gradually take a circuitous path and you will end up here, this hilltop. Because the gradient at different points will be this. Now, you notice that you started out in a direction not towards the center, but you got pulled in by the center of P. Why is that? Because if you are here, let's say that you are here, or you are even here, let me call these points little theta 1, theta 2, theta 3, or no, x1, x2, location should be x1, x2, x3, x3. Let's take any of this. Suppose you are at x2. At that moment, what would be the direction that you should go where the influence of Q is very far? You have already landed pretty close to P cluster. So P is having a pretty strong attraction on you, isn't it? It's convincing you that here, we are all here, we are all here. And so you will end up taking a path that attracts you to the center. Would you agree? Because that place would be the most illuminated, the center of the layer. So therefore, very intuitively, this point is called an attractor. This is called attractor. So you ended up here, all in good, and you just stay here. Then what you do is you say that, so what is the cluster then? Where in a very intuitive sense, you say cluster, just like a city town, is what is the boundaries of the town? It is till it gets dark enough. Right? So there is a certain level of darkness, like it's not lit up anymore. You say, okay, stop. Beyond this is the boonies, right? You leave it aside. And that's exactly what you do. When the intensity of light, the density of light overall decreases sufficiently, you say, okay, this is the boundary of my cluster. So now that the P cluster has been discovered, what remains now? The Q cluster. So take P completely out of the picture. Start with any other random point. Doesn't matter where. Now, so imagine that all the P, the light bulbs have been switched off. Right? You start with any other point. Let's say that you started a next point. I'll just start with point B. If P cluster lights are all gone and P is not visible, right? Now you realize that this will make a pretty much a beeline to go to the second attractor, isn't it? And you'll end up discovering the second cluster. This is, see people, this going in the direction of a gradient is often called hill climbing. Hill climbing, right? So when you are on a hill, when you're hiking, if you follow the direction of steepest increase, what ends up happening? In practice, you tumble, but in imagination, you're climbing to the top of the hill. Right? So that's that. So now this, yeah.
For B, why are we saying that there is no illumination from P?
Because you go, the moment you discover an attractor, you take the attractor and all its points as one cluster and you take it away. Now you will do the exercise all over again with all those points gone. P is gone. Right? Go ahead.
So was not B was existing?
No. Now you randomly pick another point.
Okay.
And you could see, if you're lucky, you might end up picking a point inside the Q cluster, but I'm deliberately taking worst case situations. You somehow are unlucky, and whenever you start, you end up in the jungle.
It could very well be the case, even though we are saying P is gone.
Yeah.
For B,
Mhm.
now it's going to move towards Q.
Yes.
But it could very well be the case that in fact B could possibly have gone to P because of the distance.
Yes. If P was not gone, it is likely. If P was not gone, it is likely that it would have made its way here. Right? It would have made a circuitous route because it would have had the attraction from Q also. So it would have gone something like this route. It would have taken this circuitous route to B, isn't it? So it doesn't matter. See, the point is you want to discover the clusters. So what is your goal? You discover two attractors. Each attractor gives you a cluster. Now, density-based clustering has many advantages. One crucial advantage that density-based methods have is they scale very well. Secondly, do you notice that they don't call outliers as members of the cluster? Between the clusters, I threw in these so-called outlier points, which legitimately shouldn't belong to a cluster, right? It is some millionaire living on a hill on his private mansion alone, right? You don't say that they belong to the city, right? Well, part of the city or something like that. So density-based clustering has the advantage that it finds true clusters and it also identifies outlier. As a byproduct, it becomes an outlier detector or anomaly detector, which has huge value for fraud detection or medical research and many, many other situations where you want to detect outliers. So I noticed that it's 880. There is another way of clustering, doing density-based clustering. It is called dbScan. It is actually the more popular one that people mention, but I didn't mention that. I'll do it in the lab when I do the lab, or maybe I have time to do it. Let me take out time and do the dbScan, which is a little different argument. So I'll give you the same clusters. Let me make the same approximate cluster. So dbScan starts with basic mathematics. It says that pick a point, pick a point, xi, and then choose a number. Let's say I choose number 5, and choose an n, and choose a points, n points. How many points? Let's say 5, and choose a epsilon neighborhood, epsilon distance. Let's call it epsilon is a distance. A very tiny distance. That's why whenever mathematicians mean tiny, they use the word epsilon. Right? Let us say it is some value. Let's say 1 unit, 1. Then what you do is, suppose you are looking at a point xi here. You make a circle around xi of that radius, epsilon radius. So I will make a circle, and I'll cheat a little bit because I took this one. Okay, so you will make a circle around epsilon, and you will ask around xi, are there at least 5 points inside that circle? If there are 5 points, you call it an interior point. So you say the statement formally is that if xi has n points, now I'm generalizing from 5 to n points, within its epsilon neighborhood, it is an interior. All you have to do is find an interior point. And then what you do is, here's the argument you do. And I'll just blow up xi here to say, suppose this was, and there are points around it. So obviously, some points are within its epsilon neighborhood. Any point within epsilon neighborhood, I misspelled neighborhood, neighborhood, okay. Neighborhood is reachable, directly reachable. So directly reachable, one simple intuition is, if your feet, like if your step size is 1 unit, epsilon log, it means that in 1 step, you can reach those neighboring points. So it is directly reachable. But there are other points which are reachable from the points that you have reached. So I can go from here to this point that is reachable. And from this point, I can go to this point that's reachable, this point, this point, this point, this point. You realize that after that, you can start reaching other points which are reachable. Now, those points also have their reachable neighbors, right? This. So this also will have its neighbors. So you keep accumulating points. Once you find an interior point, any point that you're finding as reachable from an interior point, multi-hop reachable. Accumulate all the multi-hop reachable points. All the multi-hop reachable points. Once you're done and you can't find any more points to reach through epsilon neighborhood, right? When you are done, you have discovered one cluster. And that makes sense. If you really think about this picture, what will happen if you start scanning and scanning and scanning and scanning and scanning and accumulating and accumulating and accumulating. But you can't cross over this big sea in between the clusters, isn't it? You won't be. You would be limited right here. So then, using this technique, you can discover a cluster. Then take these clusters out of the equation and start all over again. Go hunt for another interior point. Right? That will help you discover the other cluster. And whatever remains are the outliers. Right? Because if you start from this point, you realize that it doesn't have any neighbors. It's an outlier. So you just, whatever remains are the outliers. So these are all density-based clustering algorithms. DBScan is actually is supported in scikit-learn library. Today we are going to use it, and I'll show you the illustration. And we are getting to the break time. I will let you guys ask questions. Any questions, guys? I don't know. Was it simple enough to understand what I explained? Right? So we learned 3 clustering algorithms: k-means clustering and density-based clustering using DENCLU and DBScan. We'll take a 10-minute break. So we're going to do a lab on clustering. Let's see how good those labs are, like the clustering algorithms do when we apply the techniques. So we'll take a simple data set. Yesterday we talked about, or day before, we talked about the Old Faithful geyser. Just to recap, do you remember this data visualization for eruption time? So on the x-axis is how long does the Old Faithful geyser erupt? And the longer it erupts for, the more at the end of it, it is depleted of energy, and it takes longer for it to replenish that energy before the next eruption happens. So the wait time increases. And this is a plot of wait time as in correspondence with eruption, the duration of eruption. So clearly, the human eye can see 2 clusters, isn't it? Let us see what happens when we apply k-means clustering to it. So remember, I said that you apply k-means clustering, and you don't know how many clusters there are. So you need to search for different values of k. So here in this code, you will see that I'm searching for many different values of k. K is equal to 1 to 10. So I hypothesize that there may be 1 to 10 clusters. And for each clustering, I am doing k-means. By the way, which library am I using? I'm using scikit-learn, Python scikit-learn. It's very easy. And there's a k-means class. So I start with k-means is equal to 1 and all the way up to 10. What do? I fit it to the data, and then you tell predict means. It tells each point belongs to which cluster. And then you label it. And then what do? I keep track of the WSS. Do we remember what WSS was? It's also called inertia, a physics term. So then I plot it. The rest of it is plotting. So I'll just decrease the size so that we can see all 10 plots in one go, in one screen. Yes, we can see that k is equal to 1 all the way to k is equal to 9. Right? Now, look at the first cluster. It's a no-brainer, right? All the points belong to it. Right? In the second one, that looks better. Would you agree that the second cluster looks better? Third one gets worse because the third one splits a cluster. Right? The northeast cluster is getting split. The fourth one does even more splits because you're asking for 4 clusters and 5 clusters and 6 clusters. So this is the danger of k-means clustering. If you give it the wrong value of k, it will find you those many clusters, whether they are good clusters or not. So how do you get out of it? You make the scree plot, or more popularly called the elbow plot. And in the elbow plot, what do you look for? You look for the elbow, right? What is the x-axis? The y-axis is different values of WSS, and x-axis is the k, 1 cluster, 2 clusters. So where do we find the elbow? In the case of Old Faithful geyser dataset, there is a very clear elbow at 2, right? which corresponds with our intuition that 2 is the best clustering. K is equal to 2. There are 2 clusters.
Will
You
it
see that?
always produce an elbow?
Well, if the data has well-defined clusters, it will produce it. Right? Now, this is K-means clustering. Could we have done it with density-based clustering? Let's try that. And here is density-based clustering. Now remember, density-based clustering, you don't have to tell how many clusters you search for. It automatically finds good clusters. So we do that. Oh, why is it being shown again? Here we go. So once again, but it's a hyperparameter of how tiny is your epsilon, like, how tight is your neighborhood. If you make your neighborhood too tight, then you will start seeing lots of clusters. If you make it too big, right, then everything comes into a single cluster. It makes sense, isn't it? And how many points do you want to see? So those are the hyperparameters. What's your epsilon, the size of your distance, and how many points you must have for something to be called an interior point. And so clearly, this is a good clustering, this is a good clustering, this is a good clustering. And once again, there are measures to tell how good it is, the Szilard score and so forth. And if you look at this, it says that the best values are for this epsilon 0.4 and number of points is either 3 or 5. Both of them are doing pretty good. This is the one, for example, for 3. This is the one for 5. You would agree that these two are the best clusterings, are pretty good, even this one. These 3 are the best clusterings of the data, right? These 2 are really good. So this is using density-based clustering. Now you might feel that these algorithms are doing pretty good, right? Must be easy to cluster data. So I'm going to show you another data set, which I hand created just to illustrate the point. So look at this data set, or my work of art. I call it the smiley data set for an obvious reason. But of course, the machine doesn't know what it is. And we ask the machine to go find the clusters. Let's see how well K-means clustering works. Look at these clusterings. Does any one of them look good? Let's look at the first one. It says there is one cluster, right? Every point belongs to the cluster. Bad. Now look at the second one. What does that say? It says that the eyes and all the pimples belong to one cluster and yellows belong to the other cluster. Not persuasive at all. You go to the third one, again, it doesn't. You notice that the 2 eyebrows are being called one cluster. They shouldn't be. They're different clusters, right? Nose and lips are called one cluster. So you can go scan up and down and you won't find any sensible clustering. Isn't it? Is there any cluster that you can argue is good? There isn't any.
Let's say if that is the case with the real data, for example.
Yeah.
Then what do we conclude in the end?
What you conclude is, and this is a point I want to make about K-means. See, K-means work. So you ask this question, when does it work and when does it not work? You look at this data and clearly it's not working. So the question to ask is, why is K-means not working for this, but it works so well for the old faithful geyser? But why did it work for this data? This data was easy to cluster. And the answer to that is, when the clusters are globular, like sort of think of a nice round dough that you're just about to use to make pizza, right? Or anything. It's like globular structure, a deformed sphere. When it is like that, then K-means works. If your data doesn't have globular clusters, what is different about our situation now? Do you notice that the eyebrows, the nose, well, especially the eyebrows and the lips, they are not globular. And when the clusters are not globular, K-means fails to detect them. Right? That is one intuition you should carry. So if K-means is failing, it should give you an intuition that either there are no clusters, which is somewhat rare, or the clusters are non-globular. And you should try a different approach. Again, speaks to the no free lunch. So how does it show itself? Look at the scree plot, the elbow plot, and you are confused. Where exactly in this is the elbow. Can you tell where the elbow is? You could go on arguing that this elbow looks better than that, but there is no pronounced elbow, isn't it? That again is a sign that it's perhaps is not doing well. And visualization, of course, makes it obvious. So K-means didn't do well. What about DB scan on the smile? Well, or should I say, pardon my pun, the smiley dataset has wiped the smile out of the K-means cluster. So, oh no, not this one. Let's go to the smiley DB scan. So what happens with density-based clustering? This is our data, just to remind you. And, oh, look at this. How many of you feel that there are many hyperparameter combinations of epsilon and number of neighborhood points that sort of work, that just work? Isn't it, guys? It finds non-globular clusters because the only thing, the intuition it works off is density. Right? Density of points. So it works out very well. And you can see the thing. And so, guys, I just wanted to show you clustering as a phenomenon. And now what I would like to do is, in the next half an hour, I'll talk about things I didn't cover in this short course. In this course, we covered basics of what is machine learning. We covered statistical regression, correlation, causation, right? Covariance, and a few considerations like that. We talked about the center limit theorem and why it's valuable, why samples work, and things like that. Then the next day we did regression, then we did classification, we did clustering. What we couldn't cover because of a paucity of time are two more things that I wanted to cover in this short course. One is dimensionality reduction, and one is I will say these days, one of the algorithms that's very something is very popular and dominant actually. I would say that 2025, it's become front and central. It's the reinforcement learning. Nowadays, training large language models with reinforcement learning has been shown to be an extremely powerful method to make them into reasoning models, to get them to reason. In fact, a lot of your coding agents, etc. They have been trained through reinforcement learning. So I did not. And while we end the course here, I will be giving, I have to decide which days, but in the meetup sessions, I will be covering those two sessions in two separate sessions. Right? Watch out for those. If you like these sessions, watch out for that. With those, I will end my talk today.